My name is Mike Taylor. I'm a registered nurse. I'm going to call myself a complexity scientist, even though I don't have a degree, a certificate, or anything like that in complexity. I've been working with Plexus and in complexity science since around 2000 to 2001. And what I'm going to be presenting here is my original theory of health and complexity. And what I intended to be is I wanted to be a bridge, a conceptual bridge from where we are to where we may go in the future. This would connect to what Bob Heath had talked to me about previously, about wanting to build a better future for the world. And I do think that if we have a better concept of what health is, then that will help us to create that better world. I do believe complexity, as a dedicated nurse, I do believe complexity is going to give us some of the tools for that. So the group and people who are viewing this later on YouTube, feel free to use this as something to build from. Now, as I go through this, I'm going to separate out what is highly researched and highly referenced in terms of complexity material that's readily available to everyone, and what I have designed as my theory. So there's components of my theory that are, I can send you reams and reams of references in terms of complexity mathematics, complexity thinking behind some of these things. But of course, it is work that is built upon that, and it is original work, and I do intend it to be, as a bridge. So feel free to take it, build upon, not build upon. So one of the, to start out with this, and I think this is interesting because you can use it as a complexity science thought or concept. Everyone knows about the concept of initial condition, where if there's a change in initial condition, the system evolves in a different direction. And how this started was actually with a funny kind of initial condition. I started at Johns Hopkins, where I still am, because I wanted to do research in complexity and health, but I really wasn't sure where to go. Like a lot of people, a lot of us, you say, this is good, we think it has potential, but we don't really know where it's going to go. And I was working with a nurse researcher from Johns Hopkins, and I was showing her a research paper that I've been working on, and she says, well, you're going to want to define health. And I thought to myself, you mean you can do that? So I looked into it, and to tell you the truth, there is not a really good, universally accepted definition of health. I mean, we have the World Health Organization definition of health, which no one is really that happy with. And so that's kind of sparked this whole theory, is what is health from a complexity standpoint. And so that's what I'm going to be talking about. Now, when you're talking about linearity versus nonlinearity, reductionism versus complexity, I want to set it up just in case we do have some people that are relatively new to complexity and nonlinear thinking about some of the differences. And this comes from some of the work I've been doing in a book I hope to present to a publisher in late fall. And this, the title of the pop-up comes from that book, talking back to Maslow, nursing complexity and the science of compassion. And it's an interesting exercise to try to explain something this complex and unfamiliar in a simple and straightforward manner. One of the tools which I discussed with Denise before, a conceptual example and analogy, is with simply with water. So you have two situations where in one situation you have two glasses of water in a room. And one is boiling and one is absolutely frozen. Now, you can make a prediction about the future state of both of those water systems, each in separate glasses. And the prediction can be fairly precise, because you know what will happen is that both of those glasses of water will eventually become the temperature of the room. Whatever the temperature of the room is, the glasses of water will come to that temperature. And you can plot that on a graph in a linear relationship. As the boiling water gets cooler, you'll see a gradual decrease in the temperature. As the frozen water unfreezes and becomes warmer, you'll see the temperature increase until they reach the same point. The reason why that's important is because you're making a prediction in a linear system. And a linear system can only make predictions if you severely limit the number of variables. So in this case, we essentially have two variables, the temperature of the room and the temperature of the water in the various glasses. This is why you can make both a time and a temperature prediction, because you have controlled all the variables. The difficulty is that life is not contained within a glass. Life breaks free of glass. And if you take one of these glasses and spill it out on the ground, what is the water going to do? Well, we have this kind of anthropomorphic way of talking about water, and we say water seeks the best path to the lowest position. And if you were to follow the trail of water as it goes along a path in the ground, you're going to find it does not follow a straight line. Of course, it follows a very jagged line, where moment by moment, as it seeks to find the lowest level, it changes its path. And we know this, and there are references, scientific studies on this, where they have been able to show the relationship between the various molecules of water and their electric polarity, and how the polarity will pull the drop or the stream of water one direction or another, depending upon where the least resistance is. So in a sense, not in a conscious sense, but in a sense, the water is actually finding, through a nonlinear process, the best path. Now, when we're talking about this, and we're talking about the physics of this, we're talking about the concept of entropy. And the second law of physics is entropy, which says that systems will dissipate energy. Just like the hot water will dissipate its heat into the room, we know high energy will flow into areas of low energy. But there is another well-researched and documented principle that may even supersede the second law, which is called the principle of maximum entropy production, which says that in any physical system, the physical system doesn't just seek the lowest level, but it seeks the quickest path to that level. So this is from physicists, and there's, of course, people thinking about this on both sides, but it is not a trivial or at all discounted discounted physical concept that systems in general not only dissipate energy, but they look to do it in the fastest way possible. So a system doesn't explore all pathways to this lowest energy state. It seeks out the fastest. And so this work is based upon that particular physical concept of maximum entropy, about that. And then I'm going to talk about the theory and how it's built and some of the implications of the theory for health. Now, when we're talking about linearity and nonlinearity, I love the fact that the real world sends you examples all the time. This last Sunday, I was listening to an interview of Francis Collins. I don't know if you know who Francis Collins is, but he's the current director of the National Institutes of Health. And he was on the television promoting this new process nationally, where they're going to be collecting the DNA of a million Americans, and they're going to be collecting they're going to be comparing the DNA data with self-filled out health behavior surveys. So over 10 years, people are going to be filling out health surveys, saying what their health behavior is, sending that into the researchers, and they're going to, after 10 years with all this data, and they're also going to get lab work, so it's not just going to be self-reported data, it's also going to be lab work, and they're going to try and correlate all this data with how genes are related to causing disease, and how we might be able to change the course of disease through what's called precision medicine. If you've not heard of precision medicine, the concept is we can take someone's genetics, understand their genetics, and then develop some kind of intervention that will counteract what the problem with the genetics are, and the disease will be ameliorated. And Dr. Collins, who I'm sure is an extremely bright person, if he's going to be head of the National Institutes of Health, he was explaining this to the news person, and he said that, well, it's a lot like you get a precision medicine. It's going to be a lot like you get a pair of glasses for your particular correction. And a lot of us, in fact, I don't see anyone who's not wearing glasses. So we're all boomers in the same generation, and we're all wearing glasses here, all right? And he says it's a lot like that. So each one of our prescriptions matches us particularly. And he says precision medicine will be like that. The difficulty with that is he's trying to create the concept of a linear, he's trying to use a linear solution for a nonlinear system. So when I go to the ophthalmologist and get a prescription for glasses, they're looking at the particular curvature of my lens and my cornea, and what the defect is in the curve of my eyeball, and then prescribes a particular correcting curve with a pair of glasses that sits upon my nose. Okay? What it doesn't consider is that the particular curvature of my cornea and my lens is not a static system. It's actually a nonlinear system that is constantly supported by the flow of fluid and other materials through my eye. So my cornea is held in its particular curve, partially by the proteins there, but also by the flow of fluids behind the cornea. So whenever you come up with a solution, and it's a linear solution, you making the assumption that the system itself is not going to change, that the person's eyesight is going to be the same. But the difficulty is that nonlinear systems change. In fact, that's a fundamental principle. You don't have to wait for change. Nonlinear systems, that is a basic feature, is change. So in my opinion, the whole precision medicine is a little bit off, I don't think it's going to work, to put it bluntly, because you're collecting all this data on this population, and you're trying to get these correlations between different factors, but in the same time, all these people are changing, the systems are changing, and we know from research that even our genetic structure is under constant change, not from a strict evolution in terms of changes in nucleotides and things like that, but how genes are expressed, when they're expressed, how often they're expressed, and when they're not expressed. So systems are not static, and that's why linear solutions, in my opinion, don't work. Now, to go on to health, I'm going to share just one of my favorite slide. It says I'm sharing my whiteboard. Here it is. Excuse me, this is the first time I've done this. So if you look at this, this is my favorite slide from Complexity, Science, and Health. And this is in my area of diabetes. So when you do a time series of glucose tests, where you're measuring someone, say, every 5 minutes. So every 5 minutes, you're getting a new glucose value. And you watch, in healthy subjects, which is the top graph, you see that the line is a very jagged line, going up and down, even imperceptibly. Now, what you don't know, what you can't see from this particular thing, but if you look at the time series, even by the minute or like that, you can see the same kind of jagged line. There's a certain kind of self-similarity to it. What I'm going to take your attention to is the bottom slide where you have frank type 2 diabetes. Notice that the lines there become much more linear. So what's happened between the healthy non-diabetes and the diabetes individual is what has happened, and this is, again, this is all research-based, I can send you the references. What's happened is the moment-to-moment adaptation of the glucose management system, also known as a metabolic system, has become disconnected from an information cycle of the rest of the body. So the glucose management system cannot, on a moment-to-moment basis, adapt to body needs. And on the top graph, that's why you get the jagged line, because you get this moment-to-moment adaptation to what the body needs based upon the fact that the body is a nonlinear, constantly changing system. And when you get a disassociation of communication within the body, such as in the type 2 diabetes, then you get a linear line. So it is actually linearity that is a sign of dysfunction. And for Bob's benefit, and he may have come across this, a pattern, this comes from physical therapy literature, a pattern of walking that is too similar, where each step is exactly the same, is actually a dysfunctional a dysfunctional way of walking. So, I want to take comments at this point, because now the next point is to get into my theory. So I want to get any kind of feedback on whether this is theory and what they have seen in their own journey.
Well, it's complementary. This is Bob. It's complementary what I see, or in the example you gave in motor coordination, is that you're always non-linearly changing. It doesn't really show up until you get to a point of such as the phase transition between walking and running. It's a completely non-linear change that you can't even anticipate what that would look like the first time.
Yeah. Right.
And so the phase changes then become the ahas that, oh, I see this is really happening. But I agree that the more dynamic you are, the more nonlinear it is in every moment. And that's the idea of staying in the pink with Parkinson's. When you have Parkinson's, you get locked into attractor patterns.
Right. There's also research by Ari Goldberger in terms of heart rate. And when there's a lack of communication or a lack of adaptability between the various nodes in the heart, you get too much of a regular rhythm. A rhythm is a diseased rhythm. I'll take one or two other comments and then get into the theory, my theory of health. And if there are no other comments. Okay. So now the basic problem is, and of course it really kind of struck me as amazing. Here I am, I've been a nurse working in healthcare since 1982, and no one has a good definition of what we provide to people. It just does not exist. What do we mean when we say healthy diet, a healthy economy, a healthy community, a healthy anything? What does that actually mean? It's the only definitions you see tend to be either self-referential or maybe talk about resilience or something like that. So in crafting my own definition of health, I looked into what the work was on disease and complexity. So that's where I figured that if you're going to be figuring out what health is, then it may be potentially the opposite of what disease is. And when you look at the complexity literature on disease and what disease looks like mathematically in complexity, it looks like just what we've been talking about. That there is a disassociation, a lack of adaptive connection between systems. So there is a miscommunication between systems. Now, it took me a while to figure out kind of like, well, what are we communicating? So what is the information that we're adapting to, that's communicated, that we're missing out on? Exactly what is this information? And this is where I came across someone that we talked about before we started with the recording, was a Carl Friston, who's a neurology researcher out of England, Britain, and he's internationally known for what's called the free energy association between brain health and even evolution, where he says that what the information is that keeps the system working is the sharing of predictive information. And that systems, in order to maintain their integrity, need to find the best predictive solution, meaning that it has to find not what is happening now, but it has to predict what is the future state of the system, not what the current state is. Whatever is happening now is actually become history because the next moment has changed. So I had been in email contact with him, and he felt like I was on the right track with my work. I'd say my research paper I'd worked on. But then as I did more research, I noticed that his wasn't the only mathematical formula out there that did the same kind of thing. Bayesian predictability, associative plasticity, there's a number of them out there that essentially say the same kind of thing in that a prediction is taking what you know currently, trying it out in the environment, and having a process to identify what was the amount of error between what I thought was going to happen and what actually happened. Okay? And then you use that error to update your prediction. So this is where I'm going to go off of established complexity and then talk about my theory. So when I looked at complexity theory and how it approaches things, I found that there were multiple mathematical, multiple conceptual ways of talking about complexity that weren't equivalent, but they were extremely similar. And in working with Denise, she challenged me whether or not, because I can't remember the conversation now or not, what is the minimum amount of processes that have to happen for a complex adaptive system to minimize its predictive error. So in this theory, I define health as the continuous evolutionary process for the continuous minimization of predictive error. Okay? And what I say is every complex adaptive system, whether it be proteins or cells or organs or humans or economies, that there's a minimum of 3 processes that they must have in order to minimize predictive error. The first is that they have some kind of fit already with their environment, that they already have some kind of predictive model. So I'd like everyone on the call to look around and see if they see any fish swimming by their heads. Okay? If you see a fish swimming by your head, one of you is in the wrong environment. All right? If you are speaking English, you are also in the right environment, because I'm not going to do this in the German. I'm not that good at it. If you're new in complexity, this may also be a good environment for you if you're trying to learn. So when we talk about the basic model of prediction, what I've decided to do in my theory is to choose a single concept and a single mathematical pair for the 3 processes that I think that are essential. So one is Bayesian, meaning having a basic predictive model that fits with the environment. But any of us as complex adaptive systems have to then find our way in the environment. So what is the next step? And what I found was that there's a lot of different mathematical models and conceptual ways of talking about wayfinding or path selection. So systems have to find what is the next step. I've determined what the future state of the environment is. I'm going to explore the environment by taking a step. So some of the things, some of the mathematical concepts are biased random walk, Levy flights, Markov chains. These are not equivalent mathematical formulas, but they're very similar in that they talk about how a system finds its way in an environment. And so I call this finding the path. So I call it, I pair together biased random walk and finding a path. What also was obvious to me was that complex adaptive systems never come in isolation. They come in groups of similar complex adaptive systems. So when you have proteins, and I read about this because I am a geek, I just read it last week, within geology complexes, if I'm mispronouncing that, within cells, certain proteins that are responsible for transport are not just randomly distributed throughout the Golgi complex, but they actually find their way. They are self-organized. So proteins, and this really got me onto this, because here we are talking, we're having people who are writing articles in the Proceedings of the National Academy of Sciences talking about Bayesian proteins, as if proteins were making predictions about the future state. And they're saying that proteins were demonstrating a Bayesian type process. So proteins seem to be able to find a path. And how, when you get a collection of any complex adaptive system, whether it's me and my friends on this call, or proteins or cells or birds in flight, we get additional predictive information from the group. So there's also a variety of mathematical and conceptual things there. So it might be quorum sensing, or some other mathematical, it might be what's called a Markov blanket, which Friston uses. He uses the term Markov blanket, which talks about the group prediction and how it affects individual predictions. The last thing about this is that these systems have to be interconnected, and that there becomes a hierarchy of prediction. So these proteins within the cell that are wayfinding and finding similar proteins and doing their process have no idea that I'm on an international call, which will then be saved to some kind of website later on. They're just doing their thing. They're doing their prediction, unaware of my brain doing its prediction about what is the next word that's going to come out of my mouth. These kinds of things. So for me to be successful in my goal, which is to create a future state of better health, then I take all the predictions, including the cellular predictions that go all the way up to the nerve cells in my brain that are coordinated into collections and groups that make prediction about how to construct words and sentences in order to communicate things to you so that you understand in a certain way. Okay? So what I say is health is a continuously evolutionary process to the minimization of predictive error, and that every system has to have, at a minimum, these three processes, which they has to fit with. It has to be an environmental fit with like a Bayesian-like process. There has to be a method of pathfinding and a method of collective action. Okay. Now, the reason I went with this is because I thought it might be an endless process to try and find exactly the right term or the right mathematical tool. So Friston is brilliant in what his work is, but now his work is proving that particular mathematical formula. And like I said, my goal here is that I create a bridge. So I don't particularly care what mathematical formula or what concept you take away. You're free to create your own concept or your own formula for this. But what I did was that I took this concept and I looked based upon my understanding of certain actual human systems, and I applied it to human systems. And I'm going to talk about two human systems and how I applied it to these systems, and then I'm going to talk about the implications of the theory and leave it open to questions. So, and so one thing I did forget was in path selection, I noticed that paths, steps on a path seem to be divided into two types, where there was a kind of step which was a search for environmental pattern, and then another step that seemed to be a matching of environmental pattern to internal patterns. So you call this, in biology, you call it roll and run, where a bacteria tries to find our source of food. It will go through an alternating environmental wayfinding where first we'll roll, moving around semi in a random, not totally random, but semi-random search pattern. When it detects a signal, then it runs to that signal, and there's this continuous alteration between the complex adaptive system seeing the external pattern and then matching that external pattern to an internal pattern. So I say, in my theory, I say each step on the path is either a connectedness step, which means that it is a step that is a search for an external pattern of action, or a separateness step, which is that particular complex adaptive agent's matching of the environmental pattern. For instance, we know that when we look at something, our eyes do not have a miniature picture of what the computer looks like in our brain. We don't actually have a construction of a computer picture in our brain, but what we have are representations of what we've learned a computer looks like that are firings of neurons that then represents that external pattern. So the computer is external to me, and I interpret this external pattern not directly, but through a representation of neuron firing. This is something we know. So there's both internal patterns and external patterns. So I applied this to what we know about infant and child development. And I recast the stages of child development. You probably, because this is a general theory of health, it's not just specific to one particular thing like diabetes. So I say each of those classic stages is a pattern, is a pathway to increasing predictive, a minimization of predictive error. When a baby is born, it can't even coordinate its eyes. The eyes are swimming around in the head. But eventually, in 20 years, it's going to be walking across some college campus with a piece of paper in its hand saying, I'm ready to study physics or something like that. In 20 years, you can't even coordinate your eyes. Now you're going to change the world in some way. So each of the classic stages I divide into connectedness and separateness steps. And from birth to 5 months, I call that a connecting to the source. That's what I call that step. And it's a connectedness step where the brain is looking for environmental patterns, it's looking for language patterns, it's looking for who are the caregivers, it's looking for facial expressions, it's looking for sense and other kinds of things, and it's adapting to the environment. So it's looking for that source of information, and we know that when a child is born, it could be speaking Korean, it could be speaking English, it could be speaking, Swahili. But it will speak the language that it adapts to. The second stage I call naming the other, and this is a separateness stage where now the child is generally connected to its environment and starts to provide names and looks to manipulate the environment. So here you get grasping of objects, you get pointing to objects, you get the first mama, the first baba for bottle, and things like that. So the child starts to name the environment and create patterns that allow it to manipulate the environment to get what it wants. The third stage I call naming the self. This is where you undergo the beginnings of your self-identification with you get gender identification, you get a greater sense of who your name is, who you are, what your name is, and this self-identity is just in the formative stages. And what I say is the reason why a toddler gets very into no, don't do this and don't do that, is trying to protect this emerging sense of self. And so anything that is against that sense of self, it tries to defend against because it hasn't fully developed that sense of self. The stage from 3 months to 5 months is another connectedness stage I call the social self. This is where the child starts to explore social relationships, and the child creates stories where it's exploring relationships, and it has tea parties, and it invites alligators to the tea party and engages with other children, and I guess to find out that other people have mommies, not just they have mommies. And it gets a sense of the wider social environment. The stage of child development between 6 and 12 years, I call the competent self. This is where the child becomes culturally competent in either the intellectual, cultural, or religious aspects of the society and the environment they're in. That's a separateness step. Then another connectedness step which is the teenage years from approximately 13 to 19 is what I call the communal self, where they're developing their own sense of community. And finally, the adult self. So what I feel, and I'm again looking for this to be a bridge, so I'm going out on a limb here, as I feel like this theory gives us greater explanation of what's going on in that child's progressive adaptation. The other area that I applied this to was health behavior change. And this is kind of like the initial area I got started in, because I work in diabetes and we're constantly trying to change health behavior. And it's really, really hard. And what I say in this, and I'm going to cut it a little bit short, is I say that you can divide the predictive model of individuals into three basic categories. I call them sensory, referential, and transcendent. So someone operating at the sensory level, this is a connectedness level. There's a direct relationship between the self-concept and some sensory stimulus in the environment. So the core of this would be an addictive personality, where it might be alcohol, it might be gambling, it might be smoking, it might be food, it might be something else, but their self-concept is very tied into this, sensory type experience. And there's a direct correlation between the prediction of the individual and the environment, and they actually seek out the environment, and they seek out groups of people who share this experience, and they form clubs to go out to buffets and things like this. Then there's the referential, is where people create a frame of reference as their way of predicting the future state of the environment. This frame of reference can be cultural, it can be religious, it can be scientific. So in this case, the self-concept is the person actually uses the term of that frame of reference, such as I am a kosher eater, or I am a healthy eater, or I am this, or I am that, where that self-concept is very tied into a particular frame of reference. The transcendent self sees both the referential and the sensory levels as being not being flexible enough. Trying to think about how I can put this succinctly without running out of time here. But the transcendent self sees the self-concept, and there's also work from some of Friston's co-conspirators, where they look at our concept of self as a mental construction. Okay, so whether we see ourselves as, Mike who lives in Maryland, or Barb who lives in Maryland, and that kind of stuff, it is a mental construction. It is not something that can be taken out separately from what the construction is. So the transcendent level of self sees that that all these ways of making predictions are constructions, and can use those constructions, but in a more flexible way. Now, that's how I applied it, and because it's a theory of health, so it is big. But I want to go back to the to the actual definition of health and say what some of the implications are of that definition of health. So the definition of health was that health is a continuous evolutionary process of of minimization of predictive error. In any system, the better the prediction is, will be dependent upon the accuracy of the predictions from other parts of the system. So there will be a desire, just like the water flowing down the hill, there'll be a desire for the system to globally minimize predictive error. And what I found remarkable, and I'm contemplating, and this also comes from my work in diabetes, and this is not a political statement, but this is a scientific statement. It appears that humans and the bacteria that live within us have created an adaptive feedback process for the minimization of predictive error that says the best way of eating for humans is a vegetarian diet. And the reason for this is because the bacteria that feed on meat create inflammatory markers that then change our genes. Literally, they change our genes and give us heart disease and diabetes. But the reason a vegetarian diet is better for us is not because of some linear process, but because the system has come to a predictive solution, which we were not aware of, that the best way to the healthiest option is to be vegetarian. Now, we get a sense of this because we know that if people became vegetarian, then there would be less greenhouse gases. So there's a direct correlation between what humans eat and the number of greenhouse gases and global warming and things like this. So what the implication of that theory is that one of the reasons why we're going through climate change and global warming is because we're introducing error into the system, and that's changing the system. Now, this is, I'm summarizing in 45 minutes a book of 9 chapters and many, many pages with diagrams and things like this. This is where I leave it open for problems with the theory. Well, the main problem with the theory is you cannot verify it from a linear fashion. You will not find a formula that will prove, if you put in all the data, that the theory is correct. But I do believe that it is, again, like I say, a bridge or a platform for us as a group to think about health and how we might go forward to create a healthcare system that is based in complexity. So questions. And I'm going to look at chat because I haven't done that yet. Oh, thank you, Bob. I appreciate that. So questions and comments. Any, speak up.
Well, one thing I think of is, you know, in your stages of childhood development, and you know, maybe it's even an illusion that there are these stages that things emerge from one thing to the other, such as it's been shown that once a baby learns how to crawl, about a month and a half later, the ability to understand coding or gazing emerges. And so certain behaviors might be create the priming that other behaviors emerge, and we think of them as stages, but that's just our framing of that. And
right, I agree entirely, but I do think that framing. So my concept is that framing is our algorithm for understanding things better. So algorithms typically we talk about mathematical formulas, but I truly form of algorithm that we use to make better predictions.
Oh, and I agree, because that because we need something to have a foothold on to perceive things from, and so even the idea of metaphors of how we do that. The one quick other thing was that I often what transformational learning is, and that one of the definitions of transformational learning is that you look at you change the way that you look at the world. The vocabulary is different, and there's even a grieving process, because it's you can't go back. It's just like learning how to ride a bike. Once you learn how to ride the bike, you can't look at the world in the way that you just came non-linearly from.
Correct.
So yes, I agree with everything.
Thank you, Bob. John, do you have anything? I value your input. It looks like you may be trying to talk if you would unmute, but maybe not. Barb, do you have any comments?
I like this, especially when we're looking at the particular, say, of diabetes.
Right.
And I'm concerned about applying it to child development, because it's such a complex system that there's so much going on. It's almost a huge leap that I would almost stay away from child development, which is so complex that there are physical changes, there are cognitive changes, there are changes that happen socially because of the cognitive and physical changes, and it's almost too much to introduce a complex system in terms of, for people who are not used to looking at complexity, it becomes too much to condense it when you describe it. Whereas the explanation of the feedback with the predictive error, I completely got that immediately. And so it's almost, I would go straight from that to the interaction between the gut and the human bacteria, the human cells, that the gut is preparing for food, and that the whole system is either sealing up or leaky or whatever, and that because it's a relatively simple look at a complex system, and everybody can feel that, whereas the child development seemed almost not enough. But it's interesting, having read the article and then having heard you describe it, the description of how diabetes and the predictive error completely immediately got it.
Yeah, so it is. So I think that's where we as people, I consider everyone on this call and people who are doing the research a complex adaptive system. We seem to, as a complex adaptive system, in terms of evolving our understanding, we had to start with disease. We had to start with dysfunction before we could figure out healthful function. John, you did unmute yourself.
Yes, I had two thoughts while you were speaking. One is this may change the way we think of diseases like, for instance, diabetes, you know, and the labels we put on diseases. So that in the case of diabetes, you know, the holy grail is the hemoglobin A1C. Mm-hmm. And then someone puts a particular value on it. And you either have diabetes or you haven't.
Right.
And I think your theory moves us radically away from this, which is a very good thing. And also the fact that we put labels depending on what we can measure. So, I mean, is high blood pressure and hypertension really the holy grail, or it's a lot more complex than that? But because we can measure it, and then the temptation to put a figure on it we move away from this when we actually think of the way you're thinking of health and disease.
That's great, John, because Google is coming out with a device that will, through the measurement of blood pressure, it predicts with 85% accuracy who has diabetes. Not directly by measuring glucose, but by measuring dysfunction in another system.
That's right. Yeah. Yeah. And actually,
this is coming around.
My background is fetal maternal medicine, and that immediately made me think of the fetal heart rate. And it's the variability in it that goes away from health.
When it's in distress, it becomes too regular.
Exactly, yes.
Yeah. Anybody else have any kind of comments where it is? Yeah, and I hesitated to try to do this in an hour because it is a general theory of health. So to go to Bob's trying to do is, if you're thinking about a subject, if you're a health practitioner, you're thinking about a subject like child development, you can't think about the whole thing at one time. But what I'm saying is, as you study any particular aspect of child development, whether it be language or motor or social development, consider my definition of health and those three processes as a potential methodology to think about how you frame your research to get further understanding. I don't understand everything at the same time either.
Hi, it's Denise. The interesting is I've been looking at my notes, listening to you, had the wonderful benefit of being able to be in conversation and then writing some chat concepts. I mean, I think that it becomes what, for me, the model allows us to do is to really start at the smallest possible level within any one system and then look at how it becomes a fractal of a larger system or systems. And, you know, and Barb's comment about looking at it from diabetes, it started to make more sense. There was this point of reference that allowed people then to take the next leap. So the Google example you had with blood pressure being this particular app or tool that they're developing at Google, then using that as a predictive for some other disease or condition, people are then able to say, hey, if we can do it for this, here's the next leap we can take. And I think the real value is that the bridges that you're talking about, the fact that there needs to be bridges and that they exist, and how's the best way to find them and then cross them.
Right. So when you read the literature on complexity, it's very easy to get overwhelmed. But the reason I went to this particular thing was because you had child development people, protein scientists, cellular scientists, brain scientists all talk about how everything looks like it's Bayesian. So if all complex adaptive, let's say that this is a commonality to all complex adaptive systems, including in child development, and all the different levels and everything that develops may be in child development.
The other thing I think of is that the whole system, the complexity of the whole system, the assumption is that if you do it simple, that there's going to be a linear bridge from one system to multiple systems to another. And if you don't start with the initial idea that, oh, this whole thing is very complex and I'm looking for the patterns within that, you lose the ability to see how the next idea emerges. You almost have to start with this big picture idea at the get-go, and then maybe oscillate back in.
So there's a whole conversation within the complexity science community about fine graining versus rough graining and the value. And there's literally fights that go on in the literature. I frankly see them as complementary. And you need to both, look at the forest, and you need to, after that, look at the trees and then go back to look at the forest.
Thank you. Yes. So you need to be able to oscillate at least back and forth to have that perspective of where you're at in the system.
So there was a question from Plexus about what I would like from the participants and subsequent viewers. So I know that my thinking is limited based upon my biases. And Barb was the most recent irritant to my cognitive system. We had lunch. Did you enjoy lunch, Barb? Good. So I have actually changed some of the terminology within my theory. Not major changes, but minor changes, because she had some difficulty with it, and she pointed out that I also had some difficulty with it. So I am definitely looking for the feedback to refine it. But unless you come out with something, you'll never publish. If you keep on refining, you gotta, at some point, you gotta say what you gotta say.
Right.
Okay. I use this with my friends. I had dinner with friends last weekend, and he asked me about probiotics. And from my understanding of complexity, he said, "Are probiotics good for me?" And I said, "Well, these are good bacteria to put into your intestine, but it's like throwing seed down on the ground. Just because you throw seed down on the ground doesn't mean it's going to grow. If you put probiotics into an environment that's not conducive to them, it doesn't matter. They'll just pass on through." So it's not about a linear solution. Oh, I'm missing these bacteria, I add the bacteria. You have to change the environment and the participants in the environment. So I look forward to hearing from everyone. Denise, we'll get one final call for questions, and then we can end it. Any other questions or comments? I do appreciate you. I'm honored by your participation.
Thank you, Mike,
Thank you.
and everybody.
Yeah.
Cool. I'm going to end the recording now.
Okay, thank you.